In this lecture, we discuss about hyperbolic function. So let us first see what is the history and origination of hyperbolic functions. The idea of hyperbolic functions dates back to the 1760 to 1770s, arising as a analogous of the familiar circular trigonometric functions but based on the hyperbola rather than circle. Guillem- Guilherme D. L. Hospital first studies the catenary, the curve of a hanging chain, which is given by y is equal to a cos hyperbolic function of x by a in 1691, which led to the function we now call the hyperbolic cosine function. So it was first introduced by L. Hospital in 1691. Then John Heinrich Lambert in 1768 introduced the notation of sine h and cosine h, or it is called sine hyperbolic and cosine hyperbolic, and further formalized their study. By the early 19th century, mathematicians like André Marie Legendre and Carl Jacobi had developed their properties and linked to complex exponentials. So these are the brief history about the hyperbolic functions. Now let us define what is the hyperbolic functions. So hyperbolic functions are defined as follows. The first, cosine hyperbolic x, which is given by e to the power x plus e to the power minus x whole divided by 2. Similarly, sine hyperbolic x is equal to e to the power x minus e to the power minus x divided by 2. And if we know that these two values of sine and cosine, then we are also able to find out what is the tan hyperbolic x. It is nothing but the division of sine hyperbolic x divided by cos hyperbolic x, which gives us e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. Similarly, sec hyperbolic x is nothing but the 1 upon cosine hyperbolic x, which gives us 2 upon e to the power x plus e to the power minus x. And cosec hyperbolic x is equal to 2 upon sine hyperbolic x, which is equal to 2 upon e to the power x plus e to the power minus x. And finally, we have the cot hyperbolic x, which is given by cos hyperbolic x upon sine hyperbolic x, which gives us e to the power x plus e to the power minus x upon e to the power x minus e to the power minus x. Now, the very simple question arises that why they are called hyperbolic functions. So let us just discuss about this thing. Just let us see here what is the simplest equation of hyperbola. It is nothing but we know that the equation of hyperbola is x square upon a square minus y square upon b square, which is equal to 1. So let us put a and b equal to 1, a equal to b equal to 1. So we have the simplest equation of hyperbola is x square minus y square equal to 1. This is the simplest equation of hyperbola. Now let us put x equal to cos hyperbolic x and y equal to sine hyperbolic x. And if we put this x and y in the left hand side of this equation, we have what is the value of cos hyperbolic square x minus sine hyperbolic square x. This is the left hand side of the equation of hyperbola. But we know that what is the value of cos hyperbolic square x? It is e to the power x, e to the power x plus e to the power minus x divided by 2 whole square minus e to the power x minus e to the power minus x divided by 2 whole square. And if we simplify it, 1 upon 4, this is 1 upon 2 whole square is 1 upon 4. We can take outside. Now let me erase all this thing. So we have left hand side is equal to 1 upon 4, we can write down outside, e to the power 2x, e to the power 2x plus e to the power minus 2x plus 2 e to the power x into e to the power minus x minus e to the power 2x plus e to the power minus 2x and minus 2 e to the power x e to the power minus x. So now if we simplify this, this is e to the power 2x positive, negative, positive, negative, and we have 1 upon 4, 2 times of e to the power x into e to the power minus x is e to the power 0 is 1 plus this minus and minus will become plus 2. So we have 4 by 4, which is equal to 1, which is right hand side. So now this cosine hyperbolic x and sine hyperbolic x both satisfies the equation of hyperbola x square minus y square equal to 1. Therefore, these functions are called hyperbolic functions. So now let us see what are the different types of graphs which can be obtained by this uh, hyperbolic functions. So let me just go here. So now what is the graph of cosine hyperbolic ax? So just look here. This is the graph of cosine hyperbolic ax. The minimum value of cosine is 1 and maximum value can go up to infinity. Similarly, if we take what is the graph of sine hyperbolic x, so this is the graph of sine hyperbolic x. Now if we take both the graphs simultaneously, then this is looks like this. This is the graph of sine and cosine. Now let us take the graph of tan hyperbolic x. This is the graph of tan hyperbolic x. Now, if we take what is the graph of cot hyperbolic x, this is the graph of cot hyperbolic x. And if we take both the graphs simultaneously, just look here. We know that cot and tan both are opposite to each other. Similarly, if we take the graph of sec hyperbolic x, this is looks like this. And we know that sec and cos are opposite to each other. So if we draw like this, just look here. This is the graph of cos hyperbolic x as well as sec hyperbolic x. Now, what is the graph of cosec hyperbolic x? And if we mixed with the sine hyperbolic x, just look here. This is the graph of sine hyperbolic x and cosine hyperbolic of x. Let me show all the graphs. What will happen? Look here how we are getting graph of all hyperbolic functions. So now we have already seen what is the meaning of hyperbolic function and how this hyperbolic function looks like geometrically. Now let us take what are the different applications, what is the importance of hyperbolic functions. The first importance is in the analogy to circular function. Just as sine and cosine describe points on a circle, sine hyperbolic h and cosine hyperbolic h describe points on a unit hyperbola, making them essential in areas where hyperbolic geometry appears. And we have already proved that it satisfies the equation of hyperbola. Then solutions to differential equations. Many linear ordinary differential equations with constant coefficients yield general solution in terms of sine hyperbolic h and cosine hyperbolic h. Now, in the third importance is smooth transition functions. Their monotonic and unbounded nature makes them ideal for modeling growth, damping, and transitions. Then it is foundations of spatial relativity. Rapidly and Lorentz transformation can be written neatly using hyperbolic angles, or which is called rapidly. So, and the last, bridge between exponential and trigonometric functions. Via complex argument example, for example, cos hyperbolic x can be represented which as cos of ix. They tie together exponential, circular, and hyperbolic behavior. So that these are the importance of hyperbolic functions, why we are studying it. Now let us see what are the different applications of these hyperbolic functions. So first, use in the catenary curve, which was the origination of this hyperbolic functions. The shape of a hanging cable or arc is a scaled cos hyperbolic curve, and which is given by y equal to a cos hyperbolic x by a. Similarly, in heat transfer and diffusion, heat steady state temperature profiles in slabs and cylinders often involve cosine hyperbolic and sine hyperbolic terms. Now, in the signal processing, windowing functions, for example, hyperbolic secant window use sec h for minimal side lobes. Similarly, in control system, solutions to second order homogeneous ordinary differential equations, which is underdamped or overdamped responses, are expected with the sine hyperbolic and cosine hyperbolic. Now, in electrical transmission lines, voltage and current distribution along lossless lines use hyperbolic functions. Spatial relativity, time-space transformation use rapidity neta, where cos hyperbolic neta and sine hyperbolic neta replace gamma factors and velocity ratios. Structural engineering, so buckling modes of columns and deflection curves under uniform load involve sine hyperbolic function and cosine hyperbolic functions. Now, in fluid mechanics, velocity profile in laminar flow between parallel plates, plane possibly flow, incorporate hyperbolic, cosine hyperbolic x. Now, in the vibration analysis, transverse vibration shapes of beams with varying stiffness can include cosine hyperbolic and sine hyperbolic solutions. And at the last, it is also useful in applied mathematics and numerical methods, in spectral methods and conformal mapping exploit hyperbolic functions to map infinite domains into finite ones. So these are some applications of hyperbolic functions. Thank you.